Soll ich ihm was sagen? Ich habe doch gerade was gesagt. Warum soll ich schon wieder was sagen? Muss aber den ganzen Tag reden. Diese, da. Cryptography. So all I will, not all of what I will say, but much of what I will say can be found in this beautiful overview by Chris Piker, the decade of lattice cryptography. I'll add examples and some of the stuff I do in more detail, and some things I'll explain in more detail. Okay, good. So lattices and lattice problems. So today I'll talk about the basics of lattices and the lattice problems. See how far I get, that are the basics for most of today's lattice-based crypto systems. So let's start with the basic definitions. We'll do geometry, and we do number theory, and in geometry we also need distances. And I'll talk about mostly about two different distances. One is the Euclidean distance on R to the n. Everybody knows what the Euclidean distance is, I hope. And the other one is the infinity norm of on R to the n. So for every vector, it's simply the largest entry in absolute value. Okay. And then, and you see what kind of notation I use for that. And now we can talk about lattices. And an n-dimensional lattice is a subset of R to the n that has two properties. First of all, it must be an additive subgroup of R to the n. So if you have two elements in the lattice and you add them, that must give you another element in the lattice. Okay? And the second property is that the subgroup must be discrete, which means for every x in the lattice, there is a ball, an area around that point that does not include any other lattice points. That's not true for R to the n itself, because you can, for every point there is another one that's arbitrarily close. So these things are additive subgroups that are discrete. Let's look at examples. The easiest one is certainly z to the n. That's the easiest n-dimensional lattice you can kind of imagine. Okay, it's an additive subgroup because Z is an additive group and it's discrete. Oh, you know what this means. And that's why these things are called lattices, because they form regular points sets in the r-dimensional space, in the n-dimensional space. Let's look at another example, which I call e to the n. And that consists of all z in z to the n, such that if I write z as z1 up to zn, then I have that zi is equal to zj mod n for all I comma j. Okay. So these are all integer vectors where all coordinates have the same parity. All of them are either even or all of them are odd. Okay. So let's see what that gives us if we view that. So obviously p to the n is a subset of z to the n by definition. But this doesn't necessarily mean that lattices are subsets of z to the n. Okay, I can do any kinds of other things that are also lattices. Right? So if I want to view this here, let's do that. This p to the n. Here's 1, 2, 3, 4, say 1, 2, 3, 4, 5, 6, and also here. What you can imagine, you look at one line, say this one here. That has x, the first coordinate is 0, so it's even. So you pick every other point on this line. Okay? Here, it's 1. The second coordinate is 1. So you pick everything that also has the first coordinate odd. So this one's not in here, but this one is here. So, and then in the next row, it's again this one here, and so on. And here it's again this one here. Okay. So that's why how you, and you also continue this down here, right? So it's here and so on, and then it's here, 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 and similarly you have that here, here, and you have here, and you have here, here, and you have. Okay, so you get such a regular arrangement of points, and obviously this guy is also in here, right? And then yeah, this one in here, and this one in here, and so on. Okay. It's a regular arrangement of points. Okay, so are you still with me? Yes. Okay, and it's also discrete, right? You can easily see that. But to give you another example, I could also do something like maybe I would do where I have all x, comma y in R square, say, where say x is some c times square root of 2, and y is some d square root of 3, where c, comma d are in z. Okay. something like that. Okay. If you add two of them, you get again a multiple of square root, an integer multiple of square root of 2 and an integer multiple of square root of 3. So it doesn't necessarily have to lie in z to the n. Okay. So these are, and sometimes, and usually you should think not of these things as points, as vectors. Okay. And that's what we usually write. So it's this vector and this vector, and then we have this vector here and so on. Okay, and that will become clear later why we want to use that. Okay, but it needs to have this regularity. That's the subgroup structure, and it has this discrete structure as well. Okay, and then since we have this discrete structure, 0 is always included, the origin is always included in an n-dimensional lattice, which has length 0. But then there must be vectors in the lattice that are then as short as possible without being 0. Okay? Okay, because also around the origin you have a ball that doesn't contain any other points. So any point not being the origin has some non-zero length, and it has some limit from below on the length. And this thing is called the minimum distance of the lattice. Okay. So if you look at this example here, Pn, this here is 1 point of minimum distance. It's if, and these things are never unique, not even if n is 1, because with a point it's negative, has the same distance. Okay? And there are always just finitely many points of this distance. Right? Because if you draw a ball around this point here, and let it, or you draw a ball around the origin of lambda 1 that captures all of these things, but since any of these 2 points must have the minimum distance itself, there can only be finitely many inside this ball. Right? If you have a ball and you're looking at points where each pair of points has a certain minimum distance to each other, you can only pack finitely many in there. And that's why we have only finitely many of these things that are at this minimum distance. You can replace, here I use the Euclidean norm, you can do that with any other norm as well. Okay, but typically we use the Euclidean distance. Sometimes we use the infinity distance, but typically it's Euclidean or something similar to that. Okay? Okay? So that's the minimum. Why is it called the minimum distance? Well, it says that because lambda 1, this looks like it's a minimum length. It should better be called the minimum length of the lattice. But it's also like any difference between 2 lattice points has at least this distance. Right? Because if you take the difference between 2 lattice points, it's a lattice point, it's an abelian subgroup. So any 2 points have at least this distance to each other. Okay? That's why it's called the minimum distance of the lattice. Sometimes also called the first successive minimum. And that's how we generalize this. We define lambda I of L of the lattice is defined as the smallest number R such that L contains I linearly independent vectors of this norm. Okay? So it's the smallest radius of a ball that contains I linearly independent vectors from the lattice. And okay, so let's look at this guy here. So lambda 1 of P of n, well, the shortest one is really 1, 1. You can easily check that there are no shorter ones. And 1, 1 has length square root of 2. What is lambda 2? Say I want to look at P2 actually. Okay, and then we'll generalize it too. What's lambda 2 of P2? What's the smallest radius of a ball containing two linearly independent vectors? Yeah, this one, this lattice here. Yes, why?
Because if we to be lambda 1, the other vector is -1.
Yeah, this one here is linearly independent, has the same length. It's also square root of 2. Okay, let's look at lambda 1 of P5 in 5 dimensions. Hard to visualize, but it's what is lambda 1 of P5. Well, you only can look at integer vectors where all coordinates have the same parity. Yeah? Nope. Nope. 1, 1, 0, 0, 0 is not in the lattice because it has 2 odd coordinates and 3 even coordinates.
Oh, we are modulo 5. Sorry.
No, not modulo 5. Sorry. This is always modulo 2. Sorry. Not modulo 5. It's modulo, but even in that case, it would not be true. So I'm only looking at parity, either all even or all odd. Now in P5, what's the shortest vector in P5? One, 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 all ones is in that lattice, has length square root of 5, but it's not a shortest one. 2, 0, 0, 0, 0 is in the lattice, has length 2, and 2 is strictly smaller than square root of 5. And that's a shortest one. Okay? So that's 2. What's lambda 2 of P5? Yeah?
Should be also true because we have 0, 2, 0, 0, 0, and 2, 0, 0, 0.
It's 2 because you can take 2, 0, 0, 0, 0. Yet now for the second one, you take 0, 2, 0, 0, 0, 0. What's lambda 3? Yes. What's lambda 4? and lambda 5 of Pn is also 2. Okay. Keep that example in mind, because this is an interesting example, not for the 5 2's in there, but for something else, which we'll come to in a second. Okay. And in fact, what one can show that, which is, so this definition says that it's the smallest number R such that L contains I linearly independent vectors, each having norm at most R. In fact, one can show that there exist linearly independent vectors where the first one has length lambda 1, the second one has lambda 2, the third one lambda 3, and so on. And those can be different. So you really can find things that n linearly independent vectors where the first one has length first successive minimum, the second one second successive minimum, and so on. Okay. These are all classical results from the usually called the geometry of numbers. I may skip this for a second. Do I do? Well, maybe not. So let's look at a lattice in R to the n. It's always a strict subset because it cannot be R to the n itself. And then I can look at the quotients R to the n modulo L, which consists of all classes C plus L, where C is a real vector, and in the class C plus L, we have C plus V, where V is a lattice vector. It comes from the lattice. These are sets. And that's also a abelian group. It's like what you modulo n or things like that. It's just, if you take two, if you have a group, a subgroup of that group, then look at the quotient, then you also have things. So addition is simply, you add the representatives, right, as usual. And a fundamental domain of L is any subset F that for every coset C plus L contains exactly one representative. Okay. And if you look at the lattice Z to the n, okay, let's do that. Z to the n, R to the n modulo Z to the n. So every element, if, say, we have an element Z, call it Z. Let's say you have an element X in R to the n, okay? You can write X as X is some integer vector plus, say, an R, where Z is an integer vector. And by rounding down, you can always assume that R is in 0, 1 to the, oops, sorry, in this set here. Right? You just take this and you round it down, okay? So if X is x1 up to xn, z is z1 to the zn, then you simply say zi is said to be xi rounded down. Okay? That's it. Yeah? It's a unique representation. If you do the same thing, but here you set zi to be the closest integer, right? Then you get that R is in minus 1/2, 1/2. Or the other way around, yeah. Ah, yeah. Here should be an n. It's always p. And here is an n as well, of course. Okay? So these are fundamental domains. Everything else can be written as one representative from the class plus something else from the fundamental domain. Right? Yeah. Okay. Each lattice has such a fundamental domain. Okay. So here I defined a lattice by giving you a description of a property that lattice elements need to satisfy. Usually we define lattices differently by saying it's a set of integer linear combinations of certain vectors. And that's what we do here. So this is actually something that one can show. It's equivalent definition, and I won't do the definition, but when we have an abelian subgroup that is discrete, then there exists a set B1 through Bk of R linearly independent vectors. So there is no linear relationship between the vectors B1 through Bk with real numbers. Not just integer numbers, real numbers. And also not just rational numbers, no real numbers. And that makes a difference. Okay? Yeah, because if you want to see that, the number is square root of 2 and square root of 3. Over the rational numbers, they are linearly independent. But over the real numbers, they are linearly dependent. And that's our usual notion, sort of, that's what we have always in mind. In fact, the real numbers as a vector space have dimension infinity over the real numbers. Over the rational numbers. So don't think because everything's just on the line or so that's a finite dimension. That's not true. If you talk about rational linearly independence and real linearly independent, that makes a difference. So here we want, there exists B1 through Bk are linearly independent vectors such that L is exactly the set of linear integer combinations of the B1 through Bk. Okay? And in this case, B is called a lattice of L. Okay. Good. If K must satisfy that K is less than N. Okay. You could have, like, you're living in three-dimensional space like we are, but I can give you a lattice that's only on the ground floor, on the floor, right? It's two-dimensional. It's a lattice. The third coordinate is always 0. That's okay. Right? But it can never have dimension more, or this K can never be larger than N. That's because the basis vectors need to are linearly independent. Okay. One can show that a lattice L that is where K is at least N. Okay, so I should have written this when K is at least 2, not N2. It has infinitely many bases. Can easily be shown. And we usually write such a basis as a matrix with the basis vectors as columns. Okay? So they have n entries, number of rows in the matrix, and k columns. Those are the number of basis elements. And then we can say that rewriting this is simply L is B times Z to the K. Every vector in integer vector with K entries. And L is called full rank if K is equal to N. Usually we are mostly dealing with full rank lattices. There are also what I said a minute ago, that you can, in the three-dimensional space, you can have something that's on the floor. It need not be that there's always then one coordinate that's 0 or so. You can take any hyperplane through the origin, and then any regular arrangement of points in that hyperplane is also a lattice. But then again, you can sort of rotate the whole space so that this hyperplane becomes one of the planes that we usually think of. Okay, now we do something interesting. Can you give me a basis for P5? It's easy for Z5, right? That's just the unit vectors. A basis for P5.
The vectors we chose for the lengths of successive minimals.
No, that's not a basis. Yes?
Yeah, the vectors and then multiplied by the 1 divided by 2.
Say that again. That would be, for all these vectors, that would be the unit vectors. The unit vectors do not lie in the lattice. They have one coordinate that's 1, it's odd, and the rest is 0.
Can we have the dispositional spaces again?
I'm just working on it. So every element in the lattice can be written as an integer or linear combination of these elements. And they must be linearly independent. No dependencies allowed between them. That 2 times the unit vectors are not a basis because they all have even parity. And by combining vectors of even parity, you will never get a vector of odd parity. And the vector 1, 1, 1, 1, 1 is in the lattice and has odd parity.
You can swap out one of the 2 length vectors for 1, 1, 1, 1, 1, 1, 1 vector, and then have a basis, I think.
Exactly. That gives us a basis. And it's actually quite easy to see. So basis for P5, and in fact, for any Pn, is you take 2 times EI. By EI, I always denote the unit vectors, the ith unit vector. The one is in the ith position, everything else is 0. So that's from 1 to n minus 1. And then the last one I take, say here Bi is in, and then Bn is 1, 1, and so on. It doesn't really matter, as you said. You can throw out any one of them, of the 2 unit vectors, and replace it by this guy here. That works. Why does that work? So assume you have Z, which is Z1 up to Zn in Pn. How can I write this as a linear combination of these things? What I do is I take Zn times Bn plus, so I look at the last coordinate of it, and that's the one that I multiply here, that guy with. And then I do Zn minus 1 minus Zn divided by 2 times Bn minus 1 plus, and so on, plus Z1 minus Zn divided by 2 times B1. All these things are integers because the coordinates have the same parity. Okay, they are all in Z, and you can easily check that we get what we want. Okay. And if you look at this thing here, it's clear. You cannot take these 5 vectors. You have to take something with odd parity in there, in the basis. But odd parity, starting from 5, has length larger than 2. For n is equal to 4, it's square root of 4, it's 2, which means that in that lattice, you can have linearly independent vectors that are as short as possible, but they do not generate the lattice as a basis, which is something that probably the first time I heard it, I thought that that should not be true. If they're as short as possible, then sort of they should generate it, but it's not true. Short linearly independent vectors in the basis do not necessarily generate the lattice as a basis. And that's the kind of the easiest example where this is wrong. So that, yeah. Okay. Good. Okay, so as I said, there are always infinitely many basis vectors. Okay, so how can we get from one basis to another? Okay, or how can we check whether, given we have a basis, can we check efficiently that some other set of vectors is also a basis? Okay, and because as we will see, a lattice basis is something very special, and there are nice bases and there are not so nice bases. Even they can be really nasty. But at first we want to see how we can get from one basis to another. Okay, and the main concept here is that of a unimodular lattice. And we call a lattice a unimodular matrix, sorry. And we call a matrix U a square matrix with integer entries, unimodular if and only if its determinant is plus or minus 1. Okay. Equivalently, the matrix U is unimodular if its inverse is also an integer lattice. It's also an integer matrix, sorry. Okay. How can we see that they are equivalent? Maybe you go back to a linear algebra and you can see you can have this Cramer's rule by which you can actually write down the inverse of a matrix using the determinants of matrices where you delete a row and a column, but then you have a denominator. And in that denominator, you have the determinant of the whole matrix. Okay? And if you have a determinant of an integer matrix is an integer. Now we divide that by another matrix, by another determinant, and if that plus minus 1, then you also get an integer matrix. That doesn't establish the equivalence, but that is an equivalence. Okay, so that's why this unimodularity determinant plus minus 1, that's so important. Let me give you an example of a unimodular matrix in R2. R2, where is mine? Go. So an example for a unimodular matrix. The matrix 1, 1, 1, 2, that's a unimodular matrix. So first of all, the determinant of U, remember it, this times this minus this times this. It's 1. And also U to the minus 1. What is U to the minus 1? Let me just write this down so that I don't mess it up. It's 2 minus 1 minus 1 minus 1. You can easily check. But this gives you, if you multiply the two things, you get the identity. Okay. Okay. And then we have the following fact. If we have a basis for a lattice L with rank k and U in Z to the k times k, it doesn't hurt if you think always about full rank matrices and k is equal to n, but that's what's true. Did I do something wrong? Probably. That should be a +1. That must be a +1, yes. Now everything works out, which is also better what I had in my notes, but okay, so anyway, if you have a basis B and then you multiply that the basis viewed as a matrix by a unimodular matrix, and remember if that is basis, you have dimensions n times k are multiplied with something of k times k. Remember dimensions, the middle ones, you just delete, that's what you get out. So that gives you again an n times k matrix, and if U is unimodular, then B times U is also a basis. How can you see that? So here is suppose that B prime is equal to B times U, where U is unimodular. Then if, so let's say L is this L of B and V is in L of B, and say V is the sum Ci Bi, I from 1 to k, which we also can write as B times this vector C, or C equal C1 up to Ck. Usually when I write things like this, I talk about column vectors, although I often don't write them as column vectors. Okay? But then how can we write V also? We can write V is equal to B times U to the minus 1 times C. Okay? Those are, I just wrote down the identity, right? But this guy here is also in Z to the k, because U to the minus 1, if it's unimodular, is an integer matrix. If I multiply an integer matrix by an integer vector, I get an integer vector. And vice versa. Right. So which shows that V is also an L of B prime. So which implies that L of B is in L of B prime, and then you can reverse the rows of B and B prime, and you get the result.
B has size of k times k in this example?
No. No. Why should it? So B, say, is in R to the n times k. U is in Z k times k, which implies that b times u is again in r to the n times k. So
In that case, V should be. Oh no, whatever.
it just works out. Okay. So if you go here to our example, this means, so assume you have a basis for, you have a basis B1, comma B2 for lattice L. Then this is unimodular. What does that mean? I multiply this by this matrix. So B1 prime, which is B1 plus B2, and B1 prime, and B2 prime, which is B1 plus 2 times B2, also a basis. Okay?
I'm still thinking about. I think the V should be in Z times powered by N.
In R to the N. V is in R to the N, yes?
Yeah, and you just wrote V equals.
So this, I mean, just this part here is in Z to the K. Because this is a K times K vector, this is a vector of length K, so this whole thing is in, and it's in ZK because this is in ZK, and this is also an integer matrix, so the result will also be integer or integral. Okay. So this is what we have here. Okay. Okay. Which means, for example, that if I take the Z2, the lattice Z2, 1, 0, 0, 1 is a basis, right? Applying this unimodular matrix gets you 1, 1, 1, 2 as a new basis. Okay? And so on. And to give you just another example, and then you'll see what's happening. Well, we'll see that later. Here. Okay. Another example would be U, which is 1, 2, and then I take 2, 3 here. Unimodular. Okay. I take, I do here 2, 3, 3, 5. Also unimodular. I take 3, 5, 5, 8. Also unimodular. Do you see a pattern here? The numbers that appear in these things are the so-called Fibonacci numbers. So what I do here is I take Fn minus 2, Fn minus 1, Fn minus 1, and Fn. And these are all unimodular, 5 Fibonacci numbers. And now if you apply that to our integer lattice, right? So the lattice Z2, then all these things, the columns here, if you view them as vectors, they are also basis vectors for our lattice. Okay? 0, 1, 1, 1, 0, 0, 1 is a basis. Then I can multiply that thing with any of these matrices. I get that matrix back because 1, 0, 0, 1 is the identity matrix. So all these things are basis for the columns of these matrices are always a basis for Z2. Keep that in mind. Okay. Okay, then we also say that if we have, for lattice, we have a basis B, the origin-centered fundamental parallel pipette is given simply by B times minus 1 half to the n. I'll tell you what that what it is. You can also do that, not the origin-centered, but you can apply here the fundamental domain from 0 to 1. Okay. I'll show you in a second what the difference is. And then the unique representative is simply given by this. So C minus for C to the R to the N, it's a fundamental domain, and then you have C minus this thing here is actually the unique representative. Just check it out. And here I round it to the nearest integer. Okay. How does it look like? So here, it's our original thing that I had. Here would be two basis vectors. Okay. For example, you can see I did what I did here. And then you can get any linear combination. This is not the centered fundamental parallel pipette. Let me draw this in the case that 2, the origin centered. So here we have the lattice would be here by this one and this one. The origin-centered parallel pipette is this guy here. Okay, one side included, the other not. So the way I wrote it, the minus side is included. So this part would be included, this one not. Okay? The one I drew on the other side here on the slide here is the one where you have here. Okay. Okay. That's the fundamental parallel pipette. Now let's look at, in this case here, I got over to a different basis. In fact, I applied exactly this matrix here. Okay, you can see if I take B1 plus B2, B1 plus B2, I get here. And if I take B2 to be B1 plus 2 times B2, B1 plus 2 times B2, which one did I take actually? I took a different one, sorry. No, this is B1 plus B2, and then I took B1 plus 2 times B2, that's this guy here, okay? And now not the origin-centered parallel pipette becomes this guy here, this blue one, okay? The interesting thing is, which I don't have on, the volume of these two things is the same. And that is because often mathematicians forget that to tell students the determinant of such thing here, the determinant of these two vectors in absolute value is exactly the volume of this area. And now two bases differ by unimodular matrix, which has determinant plus minus 1. Hence, it doesn't change the volume of the parallel pipette. The volume of the parallel pipette is an invariant of a lattice. It has nothing to do with a matrix representation. It's always the same. It's just the value of the It's an invariant of a lattice. If you look at these things here, right? So this is our first basis, 0, 1, 1, 0. The next one would be this guy here, right? This, and then I have B1 and 2 times B2, which would be this guy here, right? And then you can do the parallel pipette. The next one, and you can see that the parallel pipette sort of gets skinnier, right? If you take this one, it will get even skinnier, and so on. It really gets a parallel pipette that looks thinner and thinner. But the volume, of course, it gets longer and longer to make up for the thinner and thinner, because the volume must be the same. Okay. But you probably will agree that if I look at these two bases here, this one looks nicer. Right? And if you look at these things and think of this parallel pipette that approaches basically a line segment, would be much nicer to have this guy here. Okay? So, and that's what I said, because you have nice bases and you have not so nice bases. And actually that will be one of the constant themes in lattice-based cryptography, kind of. Okay. Maybe I don't want to go to this today. Let's forget about the dual lattice for the time being. I'll get to it when we need it. So now we can define certain computational problems on lattices. Okay? And now we sort of, as we did with the lambda 1, we combine number theory. So the point is, why are lattices so interesting? They combine geometry, because we live in R to the n. We have distances. We can talk about orthogonality. We can talk about angles between vectors and stuff like that, right? But we are not just talking about geometry, because in a lattice, we want this discrete structure. Okay, or if you go back to the basis, we have this restriction that the coefficients in the representations are integers, okay, not just real numbers. And that's why we leave linear algebra and geometry and come to number theory. Number theory is, at the very heart of number theory is integers, okay, or are integers, okay. And lattices combine these two things, geometry and number theory, and that's why these things are often called the geometry of numbers. Okay. Good, so, and then we have the following problem. I'll give you a basis of some lattice of B and lattice L of B, and your task is to find a shortest non-zero vector. Okay. So one that has lambda 1 of L as its length. Okay. People often think that, well, why can't I just use rounding? Okay, I get a point somewhere and I round it to the nearest lattice point, but simply by rounding all the coefficients or something like that. Well, or no, forget that. I take that back. That was too fast. Forget it. Forget what I just said. Okay, so we want to find the shortest non-zero lattice vector. The other one is approximate shortest vector problem. Here we relax the problem. You don't have to find a shortest non-zero lattice vector, but a short one. that is shortest up to some factor gamma of n. N is the dimension from which this, so it's a function of n. It turns out that this is the right thing to do. Okay, we don't need to worry about entries of b or so. It's really n, the dimension that makes things interesting. Okay. And here is a decisional version, decisional approximate SVP, called gap SVP gamma. I give you a basis of an n-dimensional lattice where I'll promise you that the lattice either has lambda 1 of L is at most 1, or it's at least gamma of n. Gamma of n is a function here, and suppose for that time, for this case here, that it's really strictly larger than 1 for all. And you have to decide which is the case. You don't have to give me a vector, you just have to tell me in which of the two classes of lattices we are. You don't have to find any proof for it, just tell me, but you have to be correct. Okay? So you can imagine that this, say, gamma of n is n itself. So it's either 1 or n. You either get a promise from me that you get one lattice that satisfies this, or for the lattices that have something like square root of n or so, you can output whatever you want. You need not be correct. Only in these cases you need to be correct with your answer. Okay? So this is gap SVP gamma. That's not what I want. Okay, I forgot one. So what you can also define, and that's why I want to tell you, because this is why things can be really difficult. CVP stand for closest vector problem. Which is defined as follows. I give you a basis B, and I give you this lattice, L of B, and say this is really of rank n, of full rank. I don't want, okay? And then I give you a full rank n. And I give you a T which is in R to the n. Okay? And you have to find V in L of B with that minimizes the distance of W minus T or W in L of B. You have to find a vector that is a lattice vector that is as close as possible to your target T. The target can be anything in R to the n. Yeah? No, that yeah. You want this here? I can never make up my mind whether I that minimizes this over all lattice vectors. Okay. And let's go here and sort of assume you have this basis here. You get a lattice point. Probably what will work is you get a lattice point, round down all coefficients, which means that the lattice T can be written as a real combination of the BIs with real coefficients. Just round the coefficients to a nearest integer. And that's, and in this case, if you have this lattice basis here, that's probably going to work. If you do it for this basis here, it's not going to work. Right? If you have a point here, where you probably round it to this one, because you have given it as a combination of these vectors here, of the blue ones, not the black ones, whereas the nearest point would be this one. And in fact, you can show that if you have these fundamental parallel pipettes, you would think that, well, I locate the parallel pipette in which it is, and then from the corners of the parallel pipette, I pick the closest one. And that fails. Could be anything. Could be far away from that parallel pipette, because they can be long and skinny. And that doesn't work. Okay? And shortest vector, also, you cannot simply take the basis itself that you have given here. Idea would be, well, I have a basis. Why do I not just simply pick the shortest vector I have in the basis? Think of this thing here. That can be arbitrarily far away from the truth, because you have a real bad, poor basis that consists of really long lattice vectors. And simply because they are long doesn't mean that they don't generate the lattice, as you can see here. Okay. So if you have a nice basis that one that includes, for example, a shortest vector, then you're done. If you have such a nasty basis, well, you should sort of try to find a good basis first, and then do that. Okay. Here is another one, approximate shortest independent vectors. Remember, we have these lambda 1 through lambda n, and the approximate shortest independence vector, you have given, again, an n-dimensional lattice by a basis, and then you are supposed to find n linearly independent lattice vectors that are all of length at most gamma n times lambda n of L. You know that you can find n linearly independent vectors whose length is at most lambda n of L. Here I give you a little bit of slack even, quantified by this gamma. Okay. And then we come to the bounded distance decoding. That's sort of a version of this CVP, where we are given a basis again of a lattice and a target point t in R to the n, with the guarantee that the distance of t to L, so that is this minimum here, okay? The distance to its closest lattice vector is d, and you are guaranteed that this d is even smaller than lambda 1 of L divided by 2 times gamma n. Okay? Find that lattice vector that's so close, and it must be unique. Why is it unique? Gamma n is at least 1. Forget this here. There cannot be two vectors that are at most lambda or below lambda 1/2 away from it, because then the difference between the two vectors is less than lambda 1 by triangle inequality. You can sneak in the t in between. Right? So this guy is, in that case, it's unique. So it's here the closest vector where I guarantee you, look, you're really, really close to the lattice. And you can quantify that really, really close by making gamma n larger and larger. Right? If I give you a large gamma n, then the distance to the lattice gets smaller and smaller and smaller and smaller and smaller. Eventually, if gamma n is too large, the procedure that I just described, round down, all the coefficients will work. Okay? It must work at some point. But how much slack you have to give me depends on the basis that you have. It's called bounded distance decoding problem because it's a lattice-based variant. It's a lattice variant of error correcting codes, of error correcting actually. Okay. So what do we know about these problems? And they are the basis, or the hardness of these problems is the basis of our belief in the security of lattice-based crypto systems. Okay? None of these problems can be solved easily, except this one if you make gamma n large enough. If you make it 2 to the n, I can solve it efficiently. But not much better, actually. So what do we know? So all of the above problems, the approximation problems, can be solved in polynomial time if you choose gamma n to be roughly 2 to the n. It's a little bit better than 2 to the n, because what I wrote down up there is 2 to the n times log n divided by log n. And obviously, this thing here, where are you? Yeah. Log n divided by log n is less than 1. Okay. 2 logs make things smaller than 1 log. Okay. But it's not much better. So basically, we know how to solve these problems with approximation factors 2 to the n. Exponential in the dimension. Okay. If you want to have exact algorithms, so for SVP, find the shortest one. Not something that's whose length is by a factor of 2 to the n worse than the original, than the truth. Those have running time roughly 2 to the n log n. There are versions that have running time 2 to the n, but those have also space requirement 2 to the n. Whereas these things here with 2 to the n log n have polynomial space. So in practice, in theoretical computer science, we often look at time, but the thing that usually limits what you can actually do is space. If you know that, right? If you run out of space and you go to your main disk, forget it. Then space translates to time. Okay. So these are the ones that are sort of practical. You can the theta here you can do a little bit better by doing all kinds of things. This one here, behind it is a famous algorithm going back to Lenstra, and Lovash. It's 2 Lenstras. One is Hendrik, the other is Arjen Lenstra. In fact, there are 4 mathematicians called Lenstra. One is the father, the other one, the brother is Jan Karel Lenstra. The father, I always forget the name. It's 2, so 2 of them, Hendrik and Arjen Lenstra. And getting this part here, log n times log n, is based on ideas by Klaus-Peter Schnorr, basically. That you can do that as well. And other combinations. So you really have to work sort of hard to get that. And interestingly, and that's why we talk about post-quantum, no significantly better quantum algorithms are known for these problems. You can usually do a little bit better, but only involving the constants here. You can always use things like Grover's algorithm that shaves off 1/2 in the exponent, roughly. There are, in very special cases, you can do better. So this is what we know about on the positive side. So these things seem to be very difficult. And also in practice, they are still difficult. I mean, that's some problems that are difficult in theory are not so difficult in practice. Linear programming. It's difficult in theory, or, well, it's not difficult in theory, but there is an algorithm, namely the standard algorithm to solve linear programs that everybody uses. We know it has exponential running time, but in practice, it works very well. No, that's already the efficient one. Ellipsoid method, I mean, of course, the yeah. Simplex, thank you. Simplex algorithm. Simplex algorithm has worst case running time to exponential, but in practice it works very well. Here it's different. These things are really difficult always. It's really hard to solve these problems. Oops, shouldn't do that. So what do we know? But this only means so far human beings have been too stupid to do things. What can we do on the hardness side? What can we prove? And what can be proven, and that's a long line of research, which eventually showed that SVP, SIVP, and all these things are NP hard for approximation factors slightly below linear. Okay, somewhat below linear. Okay, actually, significantly below linear. There we know that they are NP hard. Under randomized reductions, forget the randomized, it's like NP hardness as you have learned them probably a couple of semesters ago. On the other hand, these problems seem not to be NP hard for approximation factors beyond square root of n. Here's little o of n. So it's a function that goes to 0 as n goes to infinity. Okay, this here is 1/2, n to the 1/2. So this is really smaller than this. Okay. What's hidden behind here is basically it's n to the 1 over log n. Here. So n to the 1 over log n, but log n is something that goes to infinity as n goes to infinity. So what does that mean? They are probably not NP hard. If they were, then we can, for those of you that are interested in complexity theory, then we can show that the polynomial time hierarchy collapses to a finite level. Okay. Good. So it's a mixed picture that we have here. We don't have very good algorithms. The quality of the algorithms is far worse than what we can prove. This here, by the way, does not mean necessarily that these things, for this factor, we should expect polynomial time algorithms. It could be that the algorithms have running time 2 to the square root of n, or 2 to the log n to 1,000, which is still impractical. Okay, so there is more between NP hardness and polynomial time. There's much more between polynomial time and NP hardness. In fact, we guess that there is an infinite hierarchy in between. But still, so as we will see, the security of lattice-based cryptographic constructions requires hardness of approximation for approximations roughly at least linear. So we do not have, for the things that I show you, we do not have any guarantees that tell us it's hard to break these in the worst case unless p is equal to np or so. Because this is n, this is square root of n. So we need hardness for which we don't think that it's NP hard. Can still be hard, but probably not NP hard. Okay. So it's a kind of a mixed picture. Okay. Yeah. Okay, good. But these are sort of the classical problems in the geometry of numbers. But they are not the ones that we directly use for cryptographic constructions. They were used 20 years ago to actually get direct constructions. What we do use today are sort of different problems that we can relate to these problems, or whose hardness we can relate to the hardness of these problems. And those problems I'll talk about next week. These are called the short integer solution problems, and one that you will love, the learning with errors problem, because that involves Gaussian distributions. But then they are very nice for cryptographic constructions, as you will see. They are very, very powerful. Okay, and that's it for today, I guess, for the time being. Any questions so far? If you didn't interrupt me in between. So next time I'll talk about the basic problems for modern cryptographic constructions, SIS and LWE. Okay, good. Then we continue next week at 2:15 again, I guess. Okay, good. Thank you.